Hi, everybody. Welcome to the second of our Nuclear Masterclass webinars. It's great to see so many of you joining us live. My name is Marina Petri. I am a professor of physics at the University of York, and my research focus is on experiments to study the properties of atomic nuclei. So now to the exciting things to this evening's event. So tonight we'll be exploring the origins of the elements and how scientists are recreating the physics from the cores of stars in particle accelerators here on Earth. I'm very excited to have here with us today Dr. Annika Lennartz. Annika is an experimental nuclear astrophysicist working at TRIUMF. TRIUMF Laboratory is Canada's Particle Accelerator Center, and it is located in beautiful Vancouver. So I will hand over to Annika, and we are really looking forward to your talk.
Hey, great. Thank you very much. I hope you can see my screen and you can hear me all right. Okay. Hearing no complaints, I would say we should get started. So yeah, we're going to talk today about our quest to understand the stars and our own origin, so to speak, by trying to recreate what's happening in stars these days and for many, many years in the past in the laboratory. So let's get started. So it's always good to start with something profound, and it doesn't really get more profound and important than this, but maybe some of you are familiar with this very famous quote from Carl Sagan about the nitrogen in our DNA, the calcium in our teeth, the iron in our blood, even the carbon in our apple pies, and everything was made in the interiors of stars and collapsing stars. So meaning ourselves, we are all made out of star stuff. And that's really something you have to let sink in for a while. It's a very famous quote, and famous enough that we at TRIUMF even celebrated our 50th anniversary by having a beer named Star Stuff we used to celebrate. So now you can, another fun fact is that really each atom in our body was built and processed through hundreds or thousands of generations of stars ever since the initial Big Bang. So we weren't just created in just one star, but it was actually the interplay of many generations that made us who we are today. So this said Big Bang, of course, I think many of you know that, but that happened about 13.8 billion years ago. That's where it all got started, and we've come a long way since. So really, at the beginning of the universe, after the Big Bang, a few minutes or seconds later, we already had the first type of nucleosynthesis happening, meaning the first formation of elements, but only the very light ones, like hydrogen or helium, some lithium, and maybe to some extent also some beryllium. But then it stopped for a long time. So we entered what we call the Dark Ages, in this representation of the universe evolution, because at this time the universe was just too opaque for any light to be emitted. It's only been later that when it became less opaque, when things became less dense, so to speak, that light was able to travel more freely, and we got out of this phase. And that's essentially the light that you observe today as the cosmic microwave background. And then after these so-called dark ages, where there was the universe was less dense, but we didn't have any stars yet. But about 180 to 400 million years back, then the first stars formed by gas cloud being pulled together via gravity, and the first formation of elements beyond the light elements was able to occur. Now, these very first stars, they were different than what we know these days from our sun. So they, so to speak, they lived fast and died very young. And what they essentially left in our interstellar medium are seed nuclei of slightly heavier elements that are very important for later generations of stars. So these very first stars, again, they were the first chemical factories of elements in our universe. formed about 180 million years in that time frame after the Big Bang. I was already saying mostly made out of these light elements, hydrogen and helium, so that we're really massive stars that didn't contain any metals. And they were really large, about 30 to 300 times larger than the sun, for example. But this was just the beginning. After that, it got even more and more complicated. And we're going to get to the details on how exactly the formation of elements happens. Now, and that is exactly our key question here in nuclear astrophysics is, what is the origin? So we know, of course, some in the first stars, and we know that it happens in our sun and other burning phases of stars. Again, these are details that we're going to go and walk through in a little while, but they also happen, of course, in some more famous and explosive scenarios like supernovae or novae explosions, which I'm sure many of you have heard of. So all of these events, they kind of eject the elements into the interstellar medium. And so these astrophysical events, they really leave imprints in our observable universe in form of the chemical elements. So, which are displayed here in this periodic table. It's just some version of the periodic table, which shows you, the color coding shows you in each box which kind of scenarios we think these elements were created in. Now, the real building block of these elements is, of course, the underlying nuclear physics. So the nuclear reactions that are happening in stars that create these elements. So that's what we're after and what we need to understand to make sense about of this abundance distribution and really piece together the puzzle of how we came to be where we are today. And that is essentially what nuclear astrophysics is. So it's the study of nuclear reactions that fuel the sun and other stars and tell us how the elements were created. And almost all of the elements found on Earth, except for the very light ones that were formed at the very beginning of the universe, are exclusively made in stars. So what do nuclear physicists actually do? Well, it's kind of a diverse team of people with different expertise and research fields. So you have, on the one hand, the astronomers who do observations, which probably have the nicest pictures and are the most famous ones. But of course, we also have people like me in the laboratory who do experimental physics. So we do nuclear physics experiments to understand the underlying reactions. And that's a topic that we're going to dive into today. And then, of course, there are people who study other signatures other than just the observables, but also signatures of elements left on meteorites in form of so-called pre-solar grains. And of course, there's the theorists and the people that put everything into a stellar model at the end of the day to really piece together all of this information into one model to predict and understand where we come from and where we will go from here. All right, so let's talk about the nuclear reactions. Now, I was told that maybe some of you are familiar with this picture, but I'm just going to go through it once more. This is a famous chart of nuclei. So if in astrophysics you don't get around looking at this chart many, many times throughout your career. So and what you see is basically a classification of the many types of isotopes that exist in our universe. For those who do, just as a reminder, an isotope is basically, we have different versions of the same element. The element is defined by the number of protons, but it can have a different number of neutrons. So you can have the same element, so same number of protons, but a different number of neutrons of that element, which gives you isotopes. So we have about 118 elements that we discovered so far, but there's thousands and thousands of isotopes that we discovered and probably a lot more to discover. Now, so what this actually is a way of classifying these many thousands of isotopes as a form of their proton and their neutron number. And that's exactly what we see here. Now, in the center, in the diagonal, is in black. These are all of our stable elements and isotopes that we know. And everything around it is radioactive. Either it can be long-lived, can be short-lived, but of course, then this is the proton-rich side and this is the neutron-rich side. So each point on this chart represents a specific isotope of some element. Now you may wonder, okay, why are you telling me this? Well, because now we can go into the details of which of these isotopes are formed in which kind of scenarios. And there's many different processes. Again, now is the nuclear physics that comes into play that form these various regions of isotopes. Everything starts at the beginning with stellar fusion, which is, I'm going to go through the steps in the normal stellar fusion cycle later on. But what we do here is in main sequence stars, anything that is about 8 to 10 times larger than our sun can form elements all the way up to iron. So in normal burning main sequence stars, this is about as far as you get. Now, then there's other processes which are kind of famous in nuclear astrophysics. One of them is called the S process that is responsible for forming all of these elements up here following the red line along the kind of valley of stability. This is a series of slow neutron capture processes that takes place over thousands of years. And again, later AGB stars, which are slightly more involved stars or massive stars, are scenarios where this may happen. Then the other process, which is responsible for making the other half of these very heavy elements beyond iron, is what we call the R process. It's a rapid neutron capture process. And that happens in these very famous scenarios like neutron or star mergers or black hole mergers, for example, but also maybe in something less insane like core collapse supernova. I mean, they're also pretty spectacular, but I think neutron star mergers top it all these days. Again, and then there's some other processes. We don't have to go into very much detail on these. There's can be proton capture processes as well to form various elements that we can't otherwise explain. So really trying to get into like the very detail of what happens in stars and how that fits into our picture of this nuclear chart. Okay, so the main takeaway here is, you don't have to follow along like and remember all of these processes, but the takeaway here is that it's a very complex web of creation that makes this chart of nuclei. And we are, of course, trying to understand that bit by bit, and that's a lot of work. Now, so I was showing this earlier. Again, other questions that we ask ourselves is, of course, we just went through the various sites that all of these elements are created in. So I'm just pointing out some of them here, where we have, of course, something that happens at the very start of the universe and the Big Bang. Anything in blue is in like lower mass stars, like our sun. Then anything in exploding massive stars is in yellow. So there's all of these many options that kind of piece together this puzzle later on. There's about 339 isotopes of a total of 94 naturally occurring elements that are found on Earth that we are made of. But of course, just something I should mention here is that, of course, this is just our current state of knowledge, right? So like a few decades ago, this chart, this color coding would have looked much different because people probably didn't know about the neutron star mergers at the time and which elements were formed there. So like the more we learn, the more this may change, and maybe even some of you at some point get involved in trying to figure out this puzzle. Now, we can understand where they're made, and we can also try to understand, trying to move forward here. Yeah. Why not every element is abundant in the same way as the other. So this is kind of a fun representation of the periodic table, just to kind of demonstrate that, for example, like the warping here of each of these boxes is an indicator for how much of a certain element we have compared to the other. So you can see, of course, there's a lot of hydrogen from the Big Bang area. There's a lot of carbon from the normal fusion cycles in stars, same for calcium. And for example, also a lot of iron. Everything else that's made in more rare processes, like in explosive scenarios and these extreme scenarios, is a lot more rare. And now, let's at least try to understand some of these abundances. To first order, why are some of them a lot more abundant than others? And that kind of is similar to asking the question, what powers stars? So again, we're looking into nuclear reactions. Okay. So here, I'm not sure if any of you have seen this in the past, but this is like a typical diagram you would see, this onion structure of stars if they have already evolved through multiple burning stages. So if a star is massive enough, it can go through various fusion cycles all the way up to iron. So we always start with hydrogen burning in the core, hydrogen to helium, then going further, helium to carbon, carbon, oxygen, all the way to heavier and heavier elements until you reach iron. And our sun actually won't get much further than carbon because it's not massive enough. And right now we're still in the main sequence, so we're still burning hydrogen to helium for quite a long time. Now, what is shown here is just the time a star usually spends on in any of these fusion cycles. At the very end, everything happens really fast. And you can see what you see here in this plot is your duration in years as a function of the initial mass of some star and what type of fusion processes we're going through. You can see that some of the last burning phases happens in just over a day. So while you stay stably on the main sequence for hydrogen helium burning for a very long time, afterwards, everything is accelerated. Okay, so I said this goes up to iron. So clearly there is a limit. And let's understand this limit, which again brings us back to understanding about these abundances. So what drives nuclear fusion in stars is really the binding energy. And what that means is kind of illustrated in this plot here. So you can imagine if you know that nuclei are made out of a certain number of protons and neutrons, and they're bound together, right, by a strong nuclear force. And if you imagine that if you were if you were weighting the individual nuclei, so the individual protons and neutrons, and then weight the nucleus after it has been combined, there is something like a deviation or a mass loss. And that energy is basically stored because you can convert energy to mass, famously told to us by Einstein. So you have a bit of a mass loss, and that is exactly what we talk about when we say binding energy. And that is important because now, if you look at this plot here on this side, you can see the binding energy on the y-axis and the mass. So the binding energy as in units of energy per nucleon as a function of the mass. You can see that the higher you go, more and more energy is released when you're fusing these nuclei together. And that goes on all the way up until iron. Iron has the maximum binding energy here. So what that means is that if you wanted to go further, if you wanted to fuse further, you would actually have to input energy rather than energy being released. And that is a huge problem for the star at this point of its stage, because you can imagine that this very delicate balance of gravitational pressure coming in from the outside and the radiation pressure as a function of this energy release is disrupted, because as soon as you stop having the energy release coming from your core, the star starts to collapse. And that's how you would end up with what we call a core collapse supernova. Okay? So again, just for the repetition, you went through all of these various burning phases. So you have now these shells that are enriched with these various nuclei, and your core has mostly iron in it. And at this point, the star does not have a long time to live. So at this point, you can see, you can imagine that all of this gravitational pressure causes the star to start collapsing. That's why we call it a core collapse supernova. And that happens until you basically reach a really dense environment, until you compress everything to the point of nuclear matter. And at this point, you can't really go any further. So what happens, you end up with a rebound shock wave. So from the initial collapse, you go as dense as you can go. And then you have the outbound going shock wave, which will then eject all of this material, all of these very many isotopes you made in these extreme environments, because you can now imagine these hot and dense environments. There's a lot of different types of nuclear processes happening, forming heavy elements beyond iron that are now ejected into the interstellar medium, and it eventually end up in some planetary disks and also here on Earth. So that's one scenario how a star may die. What's left behind here is only a neutron star or black hole, depending on the mass. There's other scenarios, though, other explosive scenarios that we're interested in. So what's shown here on the left is actually a supernova type 1a explosion. What happens here is you have a companion system, because believe it or not, but as at least 50% of the stars have a companion. If they're close enough, I'm just going to show that one more time. If they're close enough, then material from this main sequence star here can be drawn into the gravitational well of the companion star, which is usually a white dwarf. And then you have, again, many nuclear reactions happening and what we call a thermonuclear runaway, an uncontrolled thermonuclear reaction chain that will end up in the explosion of the star, which happens within this companion. And we have a different type, a very similar type, though. You have the same starting conditions, almost. The idea is, again, you have material coming from this companion star onto the white dwarf surface. And then, again, you have this uncontrolled thermonuclear runaway reaction on the surface, though, which means that the little star here actually survives. The star actually survives it. So the whole thing can go through repetition of this process. And again, eject material from the surface into the stellar medium. So this is repeated, versus in the supernova type, the star is destroyed. And this is kind of reflected in of course, the energy release that is shown up here, the difference in that. Yeah, and this is what you would observe on Earth with your telescopes. Okay, now we've talked about like all of these interesting and fascinating scenarios, but now, of course, what can we do in the lab? So how do we study all of this down here on Earth? And that is by studying what we call a radiative capture reaction. And these reactions are very significant in stellar scenarios, and many of them. And what happens is that you essentially just have the fusion of some nucleus with another one, a proton or an alpha particle, which is basically nothing but a helium particle. They fuse together, form a new nucleus under the emission of gamma radiation. And that's usually what we would kind of indicate this with, like kind of writing down the reaction this way. Now, these type of reactions, again, here is depicted what we look at kind of always in nuclear physics. You're going to get used to looking at these level schemes. So describing this in terms of the energy levels. So let's say you have the combination of your initial nucleus plus this alpha particle. Together, they have a certain energy. If they happen to have an energy that is equal to a certain level, a nuclear level, in some intermediate nucleus, excuse me, intermediate nucleus, then something that we call a resonance happens. So your probability of this reaction to happen spikes up significantly. So that's shown over here. So a cross-section is nothing else but essentially a probability for this reaction to happen as a function of its energy. If you're coming in with the right energy, your probability is massively enhanced. And that's why we're trying to measure these reactions, particularly at these type of energies, because that's what's relevant for the reaction rate in stars. So, and that's illustrated here again. So now we have a zoom in of the nuclear chart that I was showing earlier. A zoom in of the nuclear chart that I was showing earlier. You can see this very complicated web of nucleosynthesis or nuclear reactions. And a lot of them are powered by radiative capture reactions, already starting in the pp chains in stars, going through the CNO, carbon, nitrogen, oxygen cycles in stars, and so on. And of course, also in explosive scenarios, as I mentioned earlier. These are very important. They proceed relatively slowly. So usually they're the rate limiting step in these pathways. But our problem is that they're very small cross-sections, so it's very difficult to measure them here on Earth. So you have to find a workaround. So now you imagine, of course, these black ones are stable, but of course there's a lot of radioactive ones as well. And these are particularly challenging. So you can see that in red is circled what measurements have been done with radioactive isotopes versus the ones that have been done with stable isotopes, of course, a lot more. And then it's differentiated between alpha and proton captures. Now, so what we do to kind of make this better and get more information, we're going to measure these directly in the laboratory. So don't be scared of this formula. So the only thing that you kind of want to know here is that we are trying to measure a rate, what we call the thermonuclear reaction rate, which is a measure for how often particles collide under certain conditions, under a certain temperature, and at a certain energy. And what we do in the lab, we take this omega gamma quality, which is what we call the resonance strength, so the probability for the reaction. That's what we're after. And that's all you need to know here. And you can calculate that by making measurements in the lab about how often this reaction actually happens. So that's nothing else but a so-called yield. And we do that by shooting a beam of rare isotopes on some target made out of either helium or hydrogen, depending what we study. And then we measure how many reaction products are actually created and maybe also their gamma signature. And that's what we call inverse kinematics, coming in with a heavier element, shooting that on a lighter. Okay, so again, in our measurement, an experiment, we basically just measure a difference between incoming and outgoing isotopes. Okay. Again, recap, what can we learn from this? So this will help our understanding of the origin of the elements and their abundances, really the origin of Earth and its composition, and if you want to be more philosophical, the evolution of life, and of course of stars, galaxies, and the universe itself. Okay. So now we should finally get into the lab. Now you have to find a way to produce these on Earth to actually study them, right? So stars are producing them, but to study them, we have to recreate this here on Earth. And in the last couple of decades, there has been a lot of rare isotope facilities that can produce them using accelerators here on Earth. And one of them is located here in Canada, TRIUMF at the West Coast in Vancouver, which is the TRIUMF ISAC facility, and in the future also the area facility. So how exactly do they do that? So TRIUMF, again, I was saying it's located in Vancouver. This is just a picture of the entrance and our control room, where we control the pathway of the radioactive isotope beams that we're producing. And it's, of course, located in a very beautiful city. Vancouver, right at the water, is not the worst place to live. It's close to UBC University, close to the beach, and close to mountains. So you really have it all here with a cyclotron in the backyard. And we have the best sunsets, I can tell you that. But of course, speaking of that, let's get back to the stars that we study at TRIUMF. So TRIUMF is Canada's Particle Accelerator Center. At the heart of TRIUMF is a sector-focused cyclotron, which accelerates hydrogen ions to first order. Then at a certain energy, so you have a high frequency of an electrical field switching polarity. So you kind of end up with a spiral trajectory of your charged isotope, ions in there. And when you have high enough energy, you extract and you pass through a thin carbon foil to strip off the remaining electrons. And then you end up with a bare proton beam, which you can then shoot on a production target. And that's exactly what's shown in this little video here. So that's how we're producing these isotopes. So a proton beam comes into some and shoots onto a thick target material at high temperatures. And then these fragmentation, spallation, and fission processes happen in the target, breaking up these nuclei. And then they diffuse out of this hot area into an ionization region. Once they're ionized, of course, we can apply electrical fields to extract them. But now you have this cocktail of isotopes coming in there, but you just want to pick a specific one to study a specific reaction. So you have to mass separate them first. So where you're again using magnetic fields to do that. And we're doing that similarly in DRAGON, which I will talk about in a moment. So you do a mass separation here, and then send them to the various types of experiments that we have built up at TRIUMF. So the pathway comes in here, beam from the cyclotron onto the target stations. We actually have 2 of them. Then we mass separate the beam following along, and then we go, into the experimental halls right after, into various different energy regions. We talk about DRAGON today, which is in the center of the experimental hall, and we get beam energies of about 1.8 MeV per nucleon. We can also do higher, but we don't have time to talk about that today. So the only experiment that I want to talk about today is the DRAGON recoil separator, because of course, if you have an experiment that can study reactions that are happening in stars, you need to give it a cool name and then find a way to justify this acronym. And DRAGON stands for Detector of Recoils and Gammas of Nuclear Reactions. So it's actually quite fitting. And what it is a recoil, what we call a recoil separator. So I'll walk you through this. It essentially consists out of 4 different parts. You have a gas target where you're recreating the reaction. So you have a beam coming into this hydrogen or helium gas target. You induce this reaction. And then, because I mentioned earlier that the reaction probabilities are so low that most of the time nothing really happens, but you're just shooting beam through here and it makes it in. So the main part of DRAGON is now busy separating the incoming beam from your reaction product, okay? And that's what you can do with this 2 stages of separation, and we'll talk about that in a second. So that's the one thing. And as you can see here, I mentioned earlier, it's radiative. So these reactions emit gammas, which we can detect in a a gamma detector array surrounding the target. So that's also a signature for us to say, to know, okay, this reaction actually took place. And then we're sending the isotopes around and detect them at the very end. And if you detect a heavy isotope ion here and a gamma ray here, you have a coincidence, which tells you, yes, I made a measurement. And then you're just counting, okay, how many of these do I actually measure? That's your yield. And that's what I mentioned earlier, is what is required to get these property of the resonance strength to feed that into a thermonuclear reaction rate and understand, okay, to what extent do they happen, in which scenario, under which conditions. Okay. Yeah, I don't think I have much time to talk about this, but yeah, just as a close-up on what the target really looks like, where this reaction is happening. And this is a picture of the dragon gas target a little bit closer up, and you can see how the detectors are mounted around it. And here you have the various vacuum pumps to reach high vacuum here, while you have a gas inserted in the center. Okay, so now you might think, okay, what happens now? How do I really tune my dragon, so to speak? Because what we have to do in an experiment, we have to establish a tune. And we do that with our magnetic and electrical optics elements. There's a couple of pictures here. So we have magnetic dipoles and electrical dipoles are shown here. And you can even see them here in the dragon, in the old dragon logo as well as in the new one. And this is an old picture of myself as a postdoc and my postdoc colleague at the time. And of course, we did let our Professor Emeritus do the hard work and climb the ladders while we're just sitting here working on the data acquisition. But yeah, that's not typically what it looks like. It's not staged at all. Okay, so now let's think about how does Dragon work? By the way, this is a picture of the end detector, and the target is on the other side, and then you're bending it around to detect your recoils. So just think about it as some type of a spectrometer. It's nothing else but an instrument to separate ions according to a set of criteria similar to a prism, which would be the simplest type of a spectrometer. But we're not separating different spectral, not different wavelengths, but we're separating particles instead of light. And that's happening along the way here. So again, beam comes in, and then the first stage is a charge selection in a magnetic dipole. Then you focus this with quadrupoles, and the second stage is a mass selection with the with an electrical dipole with high electric fields. And then at these focal planes, we put a set of slits to then suppress anything that doesn't meet these trajectories. Okay, that's how we separate. And more specifically, the magnetic dipole, of course, what you have here is that you have the Lorentz force working on your particles, and anything that has a different charge state will not make it through a set of slits on the focal plane center, but is then has a different bending radius and will end up at a different position. So we can just suppress that. Similarly, for the electric dipole, it's a picture of what it looks like on the inside. You have this 1.5 to 2 meter long electrodes at high voltages up to 200,000 volts. The particles that are coming in, so your initial beam and the species that you're interested in, they are have different masses and slightly different velocities. And that means we can separate them because they have a similar momentum and they have the same charge state, but because they have a different velocity, they show up at they have different trajectories, and they would show up at different spots in the focal plane. So you can again suppress what you don't want to see at the end of your dragon separator. We also have something we call the eye of the dragon, which is just helping us to kind of see the beam spot in the gas target to make sure that it's nicely aligned on the center. Before we're sending it through, we have a way to look at the beam profile throughout the separator to make sure that everything is focused properly. And then at the end, we detect it in different types of detectors that are either timing detectors, or we have semiconductor detectors, or we have gas detectors, to really make sure we understand what properties do the ions at the end have, and are they consistent what we expect from the recoils. Okay, so we should definitely now get into one example of an isotope that we have measured in the past, and that is extremely interesting for nuclear astrophysicists, because I'm talking about the cosmic gamma ray emitter aluminium-26. It's a cool example because you can directly compare what you measure in the lab with observations. So what happens here is that is basically a tracer for star formation, because the decay of this isotope emits a very characteristic gamma line at 1.8 MeV. And you can basically take a picture of your map of the sky and look for that gamma signature. And that's exactly what some of the telescopes have, satellite missions have done. And you can show that, see that here on the galactical plane. So that's it's an isotope that we can actually see. So it means it's a tracer for star formation, because it has a relatively long half-life, but it is not too long-lived to be completely uncorrelated with the area of star formation, all right? And the second interesting part here is that it's also a tracer, or tells us about the early solar system by understanding the abundances of the daughter isotope, so what it decays into, based on what we can do in terms of measurements of grains on meteorites. So it really tells us about active as well as active nucleosynthesis, as well as nucleosynthesis in the early solar system. But to piece this together, we need to understand the origin of this isotope. Okay. So aluminium-26 is also extremely interesting, because I was just mentioning the gamma line at 1.8. So you can think about that as a heating source. It was actually important at the very beginning of our solar system, because already during the formation of these planetary disks and the formation of like some planetesimals prior to the formation of Earth and the other planets, there must have been some amount of aluminium-26 present at the time. It was already predicted actually in the 1950s that the heat source was required to melt some of the ice in these planetesimals to ensure that there's only a certain amount of water left on Earth. Because contrary to what you might think, is that Earth is actually not a water-rich planet, and compared to like some of the like bigger ocean planets or ice planets or something like that. And that is very crucial for making it a habitable planet. And of course, then ultimately that's crucial for the formation of life in some environment. So the gamma ray emission was crucial to melt up the ice in these early planetesimal systems. And then the formation happened at a faster, this loss of water happened at a faster rate than the formation of the planets. And that kind of ended up with the combination of elements that we have today on Earth. And I should also mention that if you're this heating source is also relevant to heat up some of the heavier elements, which can then differentiate or sink to the core. And that's, for example, how Earth has its heavier core, and you can have the formation of magnetic field, which again is its own story and what kind of role it plays in making Earth a habitable planet for life to exist. Okay, I'll skip over this, but you can ask me if you want to more about which astrophysical sites we are debating about. where it might have originated, but the goal is really to understand which sites it is made into and which reactions play a role, to then build these stellar models to make predictions about other planetary systems and where life could exist under the similar conditions based on how much aluminium-26 is present. So what we now do is, of course, on the nuclear astrophysics side, is you want to study these reaction pathways. So this is just, again, a very close-up of the nuclear chart. We're particularly interested in understanding the proton capture reactions on this, and that's indicated over here. Again, the only thing we care about is that, again, now it goes more into deeper nuclear physics. We don't really have to go into details here, but just know that there can be various energy levels that protons can be captured on, which of course makes this a lot more complicated compared to a scenario where you only have a proton capture happening on a single state. And that's kind of making this case particularly difficult. And the thing is, if you have this isotope, this kind of metastable state that is involved, it doesn't live very long, and it decays directly into the daughter isotope, which means it doesn't populate any levels in the daughter isotope, which means there will be no characteristic gamma line emitted. So that means anything that we know from our observations of the gamma line is that it doesn't tell us anything about the existence of aluminium-26 in this metastable state. So that is, of course, a bit of a problem. So we really need to understand all the details of these reaction rates, which is, of course, difficult to do in an experiment. Just imagine that you have to distinguish between a beam made out of ground state and an isomeric state. We can do that in the lab. And I'll just skip over this because I think I'm already past my time here. And please, if you have any questions about this, I'm happy to talk about that in detail. But that's one of the key things that we can do at Dragon, distinguish between those species and actually make individual measurements of the ground state rate and this metastable rate for the nuclear reaction rate calculations. And that's what this would look like in the end. So in a measurement, what we would see is a measurement of a time of flight throughout the entire separator, from target to the end detector, as well as a local time of flight between two timing detectors just closer to the end detector. And you can see that we just have about 10 events over a couple of days or a week of measurement. So you're really sitting there and waiting for recoils and events to come in so it can almost give them names. And then this is your yield I was mentioning earlier. And then you're using that to calculate a resonance strength. And again, I was pointing out the relevance of the energy earlier. So you do these measurements at various different energies, ultimately to really put together all of the information you need to calculate your reaction rate. And what we learned of this particular resonance that we measured is actually the one that's dominating the entire reaction rate. Okay, so that means bit by bit, reaction by reaction, we're piecing together this cosmic puzzle to understand the origin of the elements. And we have to combine that, of course, with stellar observations to refine our models. And we've done that for already quite a lot of reactions at Dragon, which is just, you can see them shown up here on this nuclear chart, again, which are especially relevant for explosive scenarios like core collapse super or novae that I was showing earlier. And we're still holding the records of the measurements done with radioactive beams worldwide. Okay, so I will sum up now. Basically, the takeaway is you are star stuff. In nuclear astrophysics, we're trying to study the origin of the elements, and we need input from experiments, theorists, as well as observers. This will shed light on the origin of the elements and their abundances, so our own origin. These radiative capture actions that I mentioned before are playing a crucial role in many of these explosive scenarios. And by recreating them here on Earth, we can really unlock the secrets of the stars and discover where we come from. with this, I would like to
Indeed,
thank my
Annika, thank you
collaborators,
so much for
thank you very
this
much for
very
listening,
exciting
and
talk
I
and
think
giving
I
us a
will
glimpse into,
answer some
the
questions
research
now.
that you are doing and all the exciting things that the scientists can do to actually bring, the stars and the cosmos into the lab on Earth. So thank you very much. And I'm sure I'm echoing everybody that is connected. So we have plenty of questions. I'm not sure I'll have time to go through all of the questions. But you showed, let me start by asking you, first of all, you showed us some very beautiful pictures of Vancouver and the lab. And it is indeed a very nice place to be. And people are wondering whether TRIUMF offers tours and, whether they can actually visit the
Yes.
lab.
Of course. Yeah, TRIUMF has public tours. Actually, a lot of these tours are given by our PhD students and postdocs. And I think every day at 1 p.m. we have a free public tour where everybody can show up for that. Or of course, if you know somebody around or just send me an email, I'm also always happy to make time. So we can definitely visit all of these experiments, especially Dragon that I was showing earlier. We are also building this new accelerator infrastructure called Ariel. So we're actually going to have more beam production happening in the next couple of years. So before we close up these target areas, because they are radioactive, so you can't go into exclusion areas, but because some new target stations are being built right now, there's still some areas you can enter. So depending on when you come
Excellent,
to TRIUMF,
thank
you
you.
can still
And
see
there was a
a
question
lot more
about these
than
experiments
the
that you are
average
describing with
person on the
Dragon.
tour.
What's the length of a typical experiment? Do you measure months, years, a day, few seconds? So what is the typical length of a
Yeah. Okay. So we have to apply for experiment time, of course, because as you can imagine, there's a lot of experiments at TRIUMF and a lot of people that want to have what we call beam time. So usually this experiment that I was showing for the aluminium-26, that was taken over about 2 weeks because we measured also a reference resonance that is a bit more well known before we measure something that is unknown. So in total, I think we spent 2 weeks of data taking time on that experiment. But there's also shorter experiments that happen over a day. If you have a really strong resonance, which means a very high probability to happen, and you have high intensities of your beam, then you don't need that much time. And then you can make a measurement much quicker. But of course, those are the ones that have been done and are not that interesting anymore. So there's definitely some experiments where you could say, okay, ideally I need 4 weeks of measurement time, but it's very difficult to get that because you have to apply for beam time. And at the end of the day, everybody is their
Very good,
scheduler
thank
is
you.
trying to give
And you
everybody
showed
a
this
little
very
bit
nice
to
picture of
make sure we get
you
some
playing
science
with an
output, and
oscilloscope or setting
we
up
have to
the
make the best
DAC.
of that.
So, and you also told us all about this exciting research that you are doing. But if you think of your everyday, life in the lab, how does this look like? So, and what is, the most interesting bits that you
Yeah, I mean, to be honest, during beam time, this actually sometimes looks like this. It's definitely everybody, all hands on deck during experiments. So we have our postdocs, our PIs, some external collaborators, because we're not just doing the experiments with people at TRIUMF, but from people from all over the world. Also, especially in the UK, we have collaborators with Dragon. And then everybody comes to TRIUMF for a few weeks for these measurements. So it gets really busy during those times when you're taking data. Then you're running an experiment 24/7, which means that you have about 8-hour shifts where you usually need some expert around and some students to catch up. And usually the students are worried about their first night shift when we leave them alone once everything is running perfectly and they just have to monitor and maybe call us if something goes wrong. But it's still kind of a funny feeling for them to be left alone with this responsibility at some point. So this happens during experiments, but of course, throughout the year, we also have to, of course, write our proposals. So we have to come up with these ideas for experiments. That takes some time. Then we would defend them in form of in front of committees that provide us with the beam time in the end. There is many different experiments that happen throughout the year. So we're running between about May until about December. So I'm not just working on one single experiment like Dragon. As a postdoc, of course, I spend most of my time on this, but I'm actually busy on the experimental side throughout the year. And of course, supervising students and postdocs, and then helping them with the analysis. So of course, once you made an experiment, you have a data set, then you spend a lot of time on the analysis front and trying to understand what you measured and then correlate that with some astrophysical impact. So
Thank you.
obviously that's
And when did you realize that you want to become a nuclear astrophysicist, and what is the path that one can take?
What is the path? I think I wanted to be an astrophysicist already while I was probably 14, 15, 16, something like that at school. I was always fascinated with physics and especially stellar scenarios. So I already had my little telescope back at home and kind of trying to look at the moon back then. It wasn't much better than couldn't do much more than that. So I knew pretty early that I wanted to go into physics. So, and because we're studying these nuclear reactions here, I went into nuclear and particle physics, which I studied. I did my diploma and PhD for that back in Germany at the University of Münster. And then that connection brought me over to TRIUMF, where I did then my postdoc with the Dragon recoil separator, which is, of course, as we just learned, to study the nuclear reactions happening in stars. So what you would do, of course, you would have to get a degree in physics. It doesn't always have to be nuclear physics or particle physics to get into this, but that's kind of what my pathway was. And of course, I'm interested in the experimental side. I mean, I enjoy actually, like on this picture, fiddling around with the experiment and getting everything set up, trying to interpret how my device is working, what I'm seeing, if everything makes sense, because it's different from experiment to experiment. You sometimes have different signatures you can look for depending on what type of reaction you're studying. So I like that part. So that's why I was always in experimental physics. And that kind of was my pathway. We also have students that are more focused on stellar modeling, but they also participate in experiments, so they at least get exposed to what we do in the laboratory. But they are more interested, okay, now I really want to know what exactly happens in a star, like how does what we just measured influence a reaction network, and how does that influence the life of a star? So there's many different
Thank you so much.
pathways,
There are so many questions, but there is not enough time for this. I want to thank you again, Annika, for this very, very interesting and exciting talk. So I want to thank the audience, everybody who joined us today in this very exciting talk by Dr. Annika Lennartz, and I wish you a good night. Thank you.